Good morning, good afternoon, good evening. Whenever it is that you're watching this, this is the video for AP Calc AB section 1.6. Section 1.6. Every now and then, every now and again, I have fun little history topics. So here's our first one. They're usually pretty entertaining of some sort. Feel free to pause and read through this if you want. But this is the mathematician that proved the intermediate value theorem, which is what I had to teach you in this video. Some interesting facts about him. He was quite a partier. He did have an illegitimate child with the widow of his friend. Like I said, usually there's some pretty crazy things about these mathematicians that have proved or contributed to the calculus that we'll deal with this year. So when there's entertaining things, I will let you know. So to get started into what this intermediate value theorem is, draw a function, call it g of x, such that g of 0 equals 7, and I have that point already plotted right here, g of 0 equals 7, and then the other point, g of 3 equals -10. This is not to scale, but that's okay. So there are those 2 points. Draw a function with those 2 points included on it. Any function you want, think about it, picture some different options. And then I want you to think about this true or false question. G must pass, the function must pass through all y values between the -10 and 7 outputs over that interval. So I think they could, right? That function right there, that in this section, right, just that interval from 0 to 3, in that section we pass all of the y values between -10 and 7. But does that always happen? Could some of you have thought of a different function where that isn't true? What if, I don't know, what if, how about that function? That goes through the 2 points that we're requiring, but it doesn't pass through any of the y values, or it doesn't pass through all of the y values between -10 and 7. So, right, this isn't a must. It could. So then what's required of our function g of x so that this statement was true all the time? That would be continuity, right? That function has to be continuous. So if I change the question slightly and g is continuous on the interval from 0 to 3, and it passes through those 2 points still, but now my function must be continuous. Then will I pass all of the y values from -10 to 7 if this is a continuous function? I think so. So then more specifically, is there a place where the output is 5? And that's where this dotted line is. That's at 5. So that's a continuous function. It might have a little curve in it, right? But if it's a continuous function, it'll pass through all of those y values, including 5. Okay, so that continuity piece, I hope you realize, is important for this to be a true statement. So that's kind of the intermediate value theorem. Here it is formally. Here's your notation, your definition, excuse me. If f is a continuous function, okay, on a closed interval a to b, so those are x values, right? A to b are x values. And then n is a number such that n is in between 2 other outputs. Okay, now those outputs specifically are the outputs at the endpoints of your interval. Okay, so if those 2 things are met, then there exists an x value, we're going to call that x value c, that's in our interval a to b, such that that input c produces this output n. feel free to pause whenever you need to and get that definition down. Just like the squeeze theorem, right? We're going to have a handful of theorems that are pretty important. I'm also going to draw a visual for this. So if f is a continuous function on the interval a to b, so there's my a to b x values, and then I've got the outputs, who knows where they are, but let's say that the output at a is right there, and then let's say that the output at b is right there. So those y values are f of a and f of b respectively. And then there's this number n that's anywhere in between those two y values. N is anywhere in between. Okay? If f is continuous, I'm going to connect those 2 points that I have. If f is continuous, then there exists an x value, we're going to call it c, that's in between a and b, where that output is that value n. Another way to think about it, it's like getting on an elevator. If you get on the elevator on the 4th floor and you're going up to floor 10, you are guaranteed to pass the 8th floor, right? There's no teleporting yet, so you're guaranteed to pass the 8th floor. What about the 2nd floor? Could you have gone there? It's possible, right? Some little kid was in that elevator and pressed all the buttons and made you go down first. It's quite possible. We don't know, right? And that's what IVT is telling us. It's guaranteeing something. So if this theorem isn't applicable, then we just don't know if something exists or not. Okay? So here's that formal definition and theorem. Something I want to point out, this is an if-then statement. Before the word then, you have these conditions. I underlined them in purple. These 2 things are conditions. Those must be true in order for the conclusion of this to be true. Okay, so we always want to check the conditions of our theorem first. So I just have a few examples to do, not a lot. For the given interval, find the value c that's guaranteed by the intermediate value theorem. But before we actually do that, we need to verify that the intermediate value theorem is going to guarantee this c value first. Okay, so those conditions, we need to make sure that our function is continuous. Take a look at h of x equals 2x squared plus 1. That's just a parabola. Yes, that's continuous. So I'm just going to do just a little, like, it's not formal. It never says justify or prove or anything like that. I'm just verifying that I can use IVT before I actually find what they're asking. Okay, so h of x is continuous. I know that. The other conditions, I need to look at this inequality. So I need to calculate f of a and calculate f of b. I gave you this interval right here over the interval 0 to 2. Those are your a and b values. So I need to find out the output of this function at each of those endpoints. So h of 0 and h of 2. Plug those in there. H of 0 is equal to 1. H of 2 is equal to 9. Now what we're checking is, this is your number n. Is 3 in between 1 and 9? Yes, it is. Right? So IVT is going to help me now find that value c. Okay? Because I've met the conditions, the continuity, and this inequality. So now IVT says that there does exist an x value. In this case, that's going to be between 0 and 2, where that input is going to give me an output of 3. Okay, so now how to find that c value? Well, I'm literally going to take this statement. So h of c you're going to take your h of x, but just plug c in, right, as the input, and you're going to set it equal to 3. That's all. And then we're going to solve that for c. We want to find c, right? That was our find the value c. So I'm going to subtract 1, I'm going to divide by 2, and I'm going to take the square root of both sides. Now, when I take the square root of both sides, I get two solutions, -1 and +1. However, IVT, the intermediate value theorem, is only guaranteeing the existence of this c value on this interval. So c has to be in between 0 and 2. So that means that -1 is not a c value guaranteed by IVT. Okay? Only +1. That's my only answer. All right. Now, this next example, it's the same function. Notice that h of x is the same exact thing. It's the same interval, but now I am looking for a c value where the output is -5. Well, I need to verify that IVT is going to help me. So, is it? You still have continuity, right? That's still just a regular parabola, but we compare those outputs, 1 and 9. Is -5 in between 1 and 9? No, it's not. So IVT isn't helping me do anything, and you can't go on any further. So there's no value C by IVT. Okay. All right, here's another function. Same directions. Okay, we're going to find that value C that's guaranteed, but first we need to make sure that we can actually use IVT. Let's verify this. So here's this function h of x. It's x minus 4 over x minus 1. The first condition of IVT is continuity. Well, we know plenty about rational functions. What do we know about this function h of x? It's not continuous at x equals 1. And the interval that we're looking at is from the x values of 0 to 2. So no, h of x is not continuous, so we can't do anything. So all I'm going to say is that h of x is not continuous over that interval. So we can't use IVT. We can't do the problem. Okay? Now, what I do want you to realize is, what if the interval was from 2 to 4? I don't actually know if this is going to work out, so I'm not going to complete this problem, but your discontinuity is at x equals 1. So is the function continuous over the interval from 2 to 4? Yes, it is, right? So then h of x would be continuous over that interval, and then you would check what h of 2 is, right? Like h of x is continuous 2 to 4. And so then we'd want to look at what h of 2 is and h of 4 is, and then we'd want to see, is 5 in between there, okay? And then we would proceed. Okay. All right, now here's a bigger one. We're going to now justify. So f is a continuous function. Okay, that's good, because I don't actually know what f is. I just have this table of what, five values. That's all. So f is continuous. We've got a handful of values listed below. Is there an x value c such that the output is 1, and justify? Okay, let's do a quick visual of this function. I've got 0, -10. Let's say that's there. I've got, what, 3, 2. Let's say that's there. I've got 5, 3. I've got 8, 3. Oh gosh, and then I've got 30, 21. Let's just throw it up there. Now, if I know that f of x is a continuous function, right? When you connect those dots, it doesn't really matter how you connect them as long as you just don't ever pick up your pencil, right? That's pretty boring. It could be much more intricate than that, but as long as you don't pick up your pencil, that's all that matters. So the question is there a place where the output on that function is 1? If I went from -10 up until 2, did I have to pass through where where your output equals 1? Yes, I did. Okay, so that's what we're trying to find. And now, so there's that C value, right? Can we find that C value? Think about it. You do not actually know what the function f of x is. So you cannot, like, what would you set equal to 1 and then solve for C? We can't. We cannot find C. But what we can do is we can justify that C exists. We don't know what it is exactly, but it does exist. So here's the same problem. I just cleaned up the slide. So we're going to do this formal justification. Okay, formal, right? Justify, that's a big word. Okay, the first, we've already like proved it to ourselves, right? We've convinced ourselves, but now we need to do it formally. First thing we need to do are state the conditions. F of x is continuous. All right, I apologize. I just had to pause the video because I was beckoned to go to Jimmy John's for lunch. So I was saying that we need to state the conditions just like we kind of did before. Like, there's that first example here in blue, this right here, but I need to do this much more formally. That was kind of like just a check for myself, but now with this, you know, big word justify, we need to make it a lot more formal. So I'm stating that f of x is continuous, and I also need to state that inequality. So where's my definition? This guy right here, this inequality. Okay, so I need to find the output at both of the endpoints and then throw the 1 in between them, right? So now remember that our endpoints that we're using, let me go back to my graph, we decided that this like area where the y value will be 1, it's going to happen in between these 2 points, right? So it's going to happen between an x value of 0 and then I think this was an x value of 3, right? So those are the endpoints that I need to, kind of call out, these 2 right here. So say where they came from, right? So this is f of 0, which is equal to -10. And then that's less than or equal to, this is my n value, and that's less than or equal to f of 3, which is what gives me 2 as that output value. Oh wait, I'm so sorry. You should not have n in your inequality. You should have the number 1. I apologize. Right, so I'm showing that this output of 1 is in between these other 2 outputs. But you must show where those other 2 outputs came from. Okay? All right, now those conditions have been met, so now I can make my conclusion. My 3 little dots. And I'm literally just going to regurgitate what the question was asking. There is an x value c such that f of c equals 1. Okay, just regurgitate exactly what it has asked. Now, the last thing we need to do is we need to give credit to the intermediate value theorem. we need to say that we know that conclusion by IVT. And you can abbreviate that. That is known that that means intermediate value theorem. So I'm looking for 4 parts to these IVT justifications. I'm looking for the continuity condition, that's in green, the inequality condition, that's in purple, the conclusion, that's in blue. You're literally just regurgitating what it asked you, and then a nod to IVT, that's in red. Okay, let's just do one more. This one's not a table though, it's an actual function. So this time we're going to determine if the function has a 0 in the indicated interval. And then if so, find the 0 and justify. Now, what on earth is a 0? A 0 is a y-intercept. A y-intercept is when your y-coordinate is, oh, I'm sorry, I said that all wrong. A 0 is an x-coordinate. An x-intercept, goodness gracious. I'm wanting to eat my Jimmy John's. I apologize, you guys. A 0 is an x-intercept. An x-intercept is when your y-coordinate is 0. Okay, how about that? I said that correctly. So you're looking for, does f of c ever equal 0? Is there a c value that creates an output of 0? Okay, and we're going to have to justify. So we're going to have to do everything all formal. So here's your interval, -4 to 11. Is this square root function continuous over that interval? It is. It's not continuous everywhere, right? The endpoint at -5, and then everywhere to the left of that, it's not continuous. But over the interval, it sure is. And we don't need to prove that. Like, we don't need to do any kind of continuity proof because we know so much about what these graphs look like. I am going to specifically say, though, the interval to make sure that that's still a true statement. Okay. Now I need to do the inequality. So I need to calculate what f of -4 is, as well as what f of 11 is. So plug in -4. I think that equals -2. And then let's also plug in 11. Square root of 16 is 4 minus 3 is 1. And is 0, right? That's my output. That's my n that goes in the definition. Is 0 in between -2 and 1? Yes. So now I'm going to state that inequality. So f of -4, which is -2, is less than or equal to 0, which is less than or equal to f of 11, which is 1. Okay, there's my 2 conditions. Now my conclusion, and I'm just going to restate, like regurgitate what the question was. Therefore, the function, I'll call it by name, f of x, has a 0, right? The function has a 0 in the indicated interval. So I'm going to say in or over, doesn't matter, that interval -4 to 11. Okay, I'm just regurgitating. Last but not least, give credit where credit is due by IVT. Okay, so that's my justification that the C value does exist. But now it says, if so, find that 0. Okay, so now we need to actually find what C value makes an output of 0. So that's going to look like, remember this f of c equals 0? That's basically what I'm going to do. F of c equals 0. In your f function, just replace that x with a c. C plus 5 minus 3 equals 0. And now we're just going to solve for c. That's all. So I'm going to add 3 to both sides. Square root of c plus 5 equals 3. Then we square both sides. And there we go. I've solved for c. Now double check, make sure that that c value is in the interval that you're saying it is, right? And it sure is. So we have found the c value. So I justified, that's in the blue and purple, green and red. That's your justification that c exists. But then because we actually have the function, we can do some algebra and solve for C. Okay, remember on the table, we couldn't do any algebra to solve for C. So we couldn't do that last part. Okay. All right, that is it for the notes for 1.6. You can now do worksheet 1.6.